Hi everyone, welcome to today's Value in Energy Data seminar. Today we'll be focusing on reinforcement learning in the energy sector. We have two great speakers here today. Christopher Lee will kick things off by discussing an overview of reinforcement learning applications in the energy sector and the associated challenges that come with implementing reinforcement learning methods. And then we have Dr. Zoltan Nagy, who's an expert in the reinforcement learning energy space, and he'll present on designing grid interactive smart communities using CityLearn. And his expertise lie in designing advanced control architecture to maximize the energy flexibility potential of residential buildings. And he will also be discussing the challenges of reinforcement learning implementation in the real world and how we can address these. So thanks so much to our speakers. Chris, off you go.
Hi. Sorry, Lottie. I can't see the slides.
Two seconds, Tabitha will just pop them up.
Oh, okay, sorry. Oh, okay, perfect. Sorry about that. Yeah, thanks, Charlotte, for the introduction. So we actually used to work together at the Catapult, and while I was working there, we wrote this white paper on reinforcement learning in the energy sector, where we really wanted to look at the landscape of the field and bridge a gap between academia and industry. So we thought it'd be a great opportunity to open up this webinar to go through some of the key points in the report. So the main takeaways I hope you get from this presentation are: one, to get a basic understanding of what reinforcement learning is, and two, to see its potential in enabling the energy transition. So hopefully this will be a good segue into some of the more technical and advanced topics that Zoltan will discuss later. Next slide, please. So I just want to start off with a poll to gauge the audience a bit. I just want to see how familiar you are with some of these concepts, whether you've heard of them or used them or know some distinguishing differences between them. Sorry, this is a new platform, but are the results going to be displayed here? Sorry, Tabitha, are the results going to be displayed? Maybe.
I can read out the results. So I'm just looking here now. I've seen the numbers increase. So at the top we have machine learning, artificial intelligence, 43% have answered. Supervised or unsupervised learning, 34%. Reinforcement learning, 22%, and 0% mirage learning.
Okay, perfect. Yes, sorry for that. But yeah, I guess that's kind of what you'd expect. The more general concepts like machine learning and artificial intelligence are more familiar to a general audience, and as you get a little more specific into supervised and unsupervised learning and reinforcement learning, typically maybe people don't know them as much, but hopefully you can still learn a bit from this presentation. So I actually asked ChatGPT to come up with a fictitious machine learning branch. So it gave me mirage learning. So I just kind of put that in there to see if the audience is awake and paying attention. So it looks like everyone passed that test. So moving on to the next slide. Next, yes. So it seems like some people are familiar with these, but I just thought I'd do a quick run through of the different types of machine learning. So supervised learning is a lot like how a student might learn from a teacher, where you have labeled correct answers and the teacher will tell you what's right and what's wrong. Unsupervised learning might be more similar to like reading a book where you don't have that labeled data. So you might have to identify patterns in the data and group similar clusters together. Now, reinforcement learning it also doesn't have the luxury of that or that labeled data, but it does have a reward signal that tries to optimize through trial and error. So a famous example is Google DeepMind's AlphaGo, where they developed a reinforcement learning agent to play the game of Go and beat a human champion. And you might have seen these silly looking humans animations that they're learning how to walk and they kind of fall over. So reinforcement learning is a lot like how a child might learn how to walk, where they fall over and again, and over time they learn how to stay upright longer. Next slide, please. So before diving into the details, I just thought I'd take a step back and look at how reinforcement learning, or RL, um, can help transform the energy sector. So when writing the report, we wanted to explore the different near-term use cases and future use cases. I should preface that reinforcement learning is relatively new in all sectors, but what we typically find is the energy sector lags behind others when it comes to things like machine learning, such as tech and finance. And on top of this, there are general business problems that aren't necessarily energy specific. So we really want to look at how other companies might be using reinforcement learning and maybe lean on some of those learnings. So for example, Spotify has explored using reinforcement learning to diversify its recommender systems for the customers. The Royal Bank of Canada has explored using reinforcement learning to optimize its financial trading algorithms. So contrasting this to something like an energy supplier who is also customer facing and engages with energy trading, they might be able to draw on some of these learnings for their own use cases. We're also starting to see reinforcement learning penetrate the energy sector through industrial and commercial control system applications. For example, Google DeepMind has used it to optimize its data center cooling. Also, startups like Carbon Re have used it to optimize the cement production process and reduce carbon emissions. Now, looking more so into the future and more in the research phase, that's when we start to see domestic applications like EV charging and large scale applications like the CityLearn challenge that Zoltan will talk about, which is about all those grid interactive buildings and low carbon technologies providing flexibility for the grid. And there are other challenges out there like the Learn to Run a Power Network challenge, where they're looking at how to optimize the operational cost of running a power network using reinforcement learning, such as for like the national grid. Next slide, please. So just getting into some details here. So I'll just start off with a simple example. So reinforcement learning consists of an agent interacting with an environment. So in this case, that could be something like this little robot interacting with this maze, trying to get to the end goal as quickly as possible. So every problem consists of three main components, which are the states, the actions, and the rewards. So in this case, the states could be the observed position of the robot and the proximity to the walls. And it could choose certain actions to maneuver around in the maze and then get the reward, which is probably getting to the goal as quickly as possible. So through trial and error and simulating millions of these experiences, it'll learn the optimal strategy to get to the end goal as quickly as possible. So for the energy nerds in the room, I have an energy example here. So I grabbed it from a recent DeepMind paper where they look to optimize the cooling system in a commercial building. So that's usually a chiller plant, which is similar to an air conditioning unit. So in this case, the agent is the controller, the environment is the building, and the states are the observed temperatures in the building, the temperatures outside, different flow sensors, etc. And it can choose certain actions like deciding how many chillers to turn on, what the chilled water temperature supply point should be, and it will try to do this in order to minimize the energy consumption in the system, which would be related to those rewards. Next slide, please. Now, the natural question you guys might be asking is why use reinforcement learning over alternatives? While it's a pretty complicated debate, we tried to distill it down into these four main points. So I'll just go over a few. So as we know, as the energy system is becoming more complex, as it's becoming more distributed, um, there's a lot of renewables into the system, and a lot of alternative methods like model predictive control might rely on needing to develop expensive and costly models in order to optimize the control strategy. Whereas reinforcement learning in some cases can be completely model free and just interact with the real world without the need of a model. Additionally, we've seen with ChatGPT, you can collect human feedback with reinforcement learning in order to optimize things like a language model. Or possibly you can collect feedback from occupants to learn their perceived sense of thermal comfort in order to optimize the temperature in the room. And lastly, as we introduce more intermittent renewables into the system, uncertainty increases, and reinforcement learning naturally can handle this uncertainty as it tries to maximize an expected value. So it's really taking all that data and the uncertainty from the data and the experiences and really capturing it. So alternative methods can often capture a lot of these things, but they might need to make some simplifications, or it comes at an additional computational cost and takes longer to make decisions. Next slide, please. But reinforcement learning by no means is a silver bullet, and there are many open research challenges that researchers like Zoltan are working on. So to name a few, like with a lot of machine learning problems, you need a lot of data. And unlike with AlphaGo, where you can simulate millions of games, the real world is often limited to those real-time interactions with your system. And on top of this, you have real world consequences and safety constraints that might not be present in something like playing video games. Lastly, like other machine learning, reinforcement learning is a black box. So if interpretability of your solution is important and you need to be able to explain why it makes a certain decision, reinforcement learning could possibly not be the best for this application. But there's a lot of research going into this, and potential solutions like digital twins have emerged where you can have a digital representation of your environment, so you can run those millions of simulations without the need to take those risks in the real world environment. Next slide, please. So in summary, through trial and error, reinforcement learning learns an optimal decision-making strategy. And we're starting to see reinforcement learning enter other sectors, as well as entering the energy sector through industrial commercial control systems, owing to a lot of those benefits that I described. And there's still many open research challenges that keep a lot of the domestic and large-scale applications in the research phase. But perhaps Zoltan has solved all those problems and all those challenges and will tell us that reinforcement learning is ready for tomorrow. But no pressure, Zoltan. Thanks. Next slide. Yeah, thank you. I'll hand it over to Zoltan now.
Good. Thanks, Chris. Way to set the expectations here. Let's see. All right, welcome everyone. Thanks for joining in from me as well. Thank you, Chris, for setting the stage so nicely. Let me share over here. 1 second. Can you see my screen or not? Somebody confirm.
Yeah.
Yes.
Yeah.
Okay, you see this here, right?
Yeah.
Okay. All right, let me do it that way. That way we can get going. For some reason, it shows here sort of like a bad connection. So hopefully we can power through. Let me put this into full screen. All right. All right, welcome everyone again. Let's get rolling. So the reason we start, oopsie, this is too many things here. So my group's Intelligent Environments Lab at the University of Texas. While I'm in the US, I spend most of my life in Europe, so I'm aware of challenges that are different from the hot and humid climate in Texas. I mostly lived in Luxembourg, Germany, and Switzerland, so we're aware of having to heat homes rather than cooling them. Even though obviously this summer things look a bit differently also in Europe. My group mostly focuses on, the fancy words here, intelligent human responsive energy infrastructure. Really what we're trying to do is make sense of data in a way that it's useful to people. And by making sense, we use machine learning techniques, all the three ones that Chris talked about: supervised learning, unsupervised learning, and reinforcement learning, which is the largest share, because it gets into the control part. Now, why we like doing that is because buildings consume a lot of energy, a lot of electricity. On the flip side, that also results in a lot of emissions. And so, the built environment is kind of like a good candidate to reduce our, human-made climate change impact. So this is what motivates my work. As you know, this problem will not go away, so it'll just get kind of like worse and worse unless we do something about it. So it is kind of a pressing problem. Side note, if you want, I have a folder here. You can go and download all the papers I'm showing, including this presentation, just in case you want to look up something. You don't need to write down the references. All the papers should be in that folder. So anyway, so again, climate change is happening. It will get worse unless we do something about it. So that's what my work's about. We know in terms of buildings what we need to do. I mean, we know for most of things what we need to do is, electrify everything we can do and then decarbonize the grid. I don't believe in the carbon capture that the fossil fuel industry tries to, sell us. So mostly we need to move into renewable energies, nuclear, presumably, over time. The problem with that, of course, is that you'll get a demand-supply mismatch eventually. This is the case in the California duck curve that you see here, but it will be pretty much everywhere because you have not exactly energy at the time when you need it, right? So that's the fundamental problem that you have when you're shifting the energy supply into renewables that are a little bit more stochastic. They are predictable. They're just not at the same time happening as you have the demand. So you need flexibility. Oopsie. Now, where do we get this flexibility? So my thesis or my focus of works is in residential homes. I talk a lot about single-family homes because that's a big part in the U.S. In Europe, it's also multi-family homes. They're not exclusive, but the examples I show you are single-family homes. And so the focus I'm having is to say that those are a big potential to provide this flexibility to the grid, but at the same time, it's very hard because there's so many and everybody's different, and in the U.S., different jurisdictions, and houses are built crappily and so on. So it's not exactly easy, but that's why we do it, right? So it's an untapped potential, and so what can we do, right? And so the things with buildings is over the years we've done this, right? Go back 50 years. Usually, what you do the first is improve efficiency, and this could be by building better buildings, and in Europe, this has been basically done by adding insulation to the homes, more and more insulation. So you reduce your demand by creating, by doing more with less, basically. Use less energy to meet your demand for heating. You can use more efficient gas boilers, more efficient air conditioning, and so on. That basically reduces your load. It doesn't change the shape of your load curve, so you don't really have flexibility in that sense. So then you can take the next step and do what you can do on the grid, which is to supply yourself with electricity, which is renewables, and in homes it's typically solar. And so what you get then is the mismatch that we also have on the grid, which is that during the day, if there is sun, you will get a big dip. It's great. But then during the evening, when you actually need it because you're coming home from work, then again, you're missing it. And so it's kind of like there, but then it's not there when you need it. So similar story to the grid. And at the homes, you don't have wind, which potentially could offset this local generation. So, it's a great start, but not enough in my mind. So, not saying you shouldn't do it. You should do it, but you need more. So the question is, ideally what we want is sort of like a curve that is rather constant throughout the day, really. Like when we have loads, maybe a little bit higher during the night when you don't need them, but you can use them to, preheat, pre-cool, store energy, and then you can coast through the day. And so this way you can provide a little bit more support to the grid in a sense that, you are a flexible consumer that can consume on demand, so dispatch and also reduce your on demand, which is sort of like what we call demand response these days. And so the question becomes, right, how do we get to this blue curve? How can we shape individual home demand curves efficiently? And so, because the theme of today is reinforcement learning, the focus of this is to talk about storage and control systems. So ideally, obviously, we need some way of shifting, and you can only shift if you have a buffer. And so that's the storage. It can be all kinds of storage. I will talk a lot about battery storage today because it's very simple to visualize that. It's like your battery in your phone. You plug it in, you charge it, discharge it when you need it. It could be your electric vehicle that you plug in that provide the same sort of buffer. Hot water tanks used to be done a while ago also for that. They're a little bit less effective because there's smaller loads. And then thermal storage in commercial buildings are used a lot, ice storage, things like that. In residential, that's not so useful typically. What you do have in residential homes is, for example, like I said before, preheating, pre-cooling. So using the thermal mass of your building and the thermal capacity to coast through, times of high demand is how you can use it. So I'll focus mostly on electric batteries. Just because it's an interesting topic today, but technically anything I say, we work on as well, and it's not exclusive to electric batteries. So a quick review of control strategies, which is what Chris also introduced. So hopefully it sticks like this. So the simple way, which is typically how things are done in buildings, is rule-based control. You have a set of if then else instructions. These are called sequence of operations in commercial buildings in the lingo. So you kind of like just go in and say, if this temperature is such, then do this. Open valve, close valve, open damper, close damper, and so on. Very simple, very easy to understand, but it's far from optimal. It's far from adjustable, and normally you set it, you forget it, and then you don't really know what the building's doing unless you actually actively monitor it, which rarely happens. Then the second set, which is what's called model predictive control, it's derived from optimal control theory, which is if you know your plan. This comes from process engineering in the 70s. So if you know your plan, if you know all your chemical reactions, in that case it was, if you can predict them, then you can basically create a set of sequence actions into the future, which are always optimal. And you can show it is always optimal if you know, let's say, things like your disturbance model, like how bad things can get. You can even account for that. And so it's really, really powerful. It's proven to be optimal. The problem is it is assuming you have an access to the model of your system. And that's possible for process plants because it's chemicals, and you can kind of like predict that, and it's always repetitive. So anything that's large scale and many things where it makes sense to create such a model, it's done. Like your airplanes have this, your autopilot, stuff like that. It's pretty much standard in that. But again, as Chris also said, energy industry and buildings industry is lagging behind. So MPC, when it came aboard like maybe 15 years ago in buildings, it was great to demonstrate optimality, but then pretty quickly folks realized it's very hard to get it done at scale because you need to sit down and create this model every time. And it's very hard to scale it to many buildings. So that's really the big challenge. And I'm not saying that solved with RL, but that's the premise of one of the premises of RL is that you don't need this model. And with that, you have this sense of adaptability. And so the way RL kind of works is that you move, you get measurements from your system, you do stuff to your system, you observe it, and then you learn from that, and then you get better over time. And so, and it's very much a trial error approach. And so with the usual drawback that you can actually get into some bad behavior, which you don't want. And that's kind of like where these two approaches are antagonistic. So one, it's very optimal. You can, trust it, you know what it's doing, but it's very hard to deploy and scale. RL, and so the folks working on that are folk working on making it easier to deploy with less model requirements and so on. And so the folks working on RL know that it's, it needs quite some time to learn. It needs a lot of data, and it potentially can have detrimental effects. So the safety issue is there, and the black box issue. So there's a lot of work in that direction. And so at least in the buildings, there is some sort of convergence that a mix between the two will be great. And there's some work in that, so we can chat about that later. But for now, we'll stick with RL to see what's possible. And we've done quite a lot of work in that direction. So those are the three things. It's not a and by the way, if you have really, really good rules, they will be better than any of the other two, cost effective and anything. So you kind of like have to decide where you put your money and your time and effort. So I'm not advocating for any of these, but I'm here to talk about RL today because it's an awesome approach. Okay, So again, there's a lot of algorithms, and there's a lot of sort of ways to classify them. One is up here, model based versus model free. And that approach is the biggest one. And model-based RL is very similar to MPC in the sense that you actually do have access to a model, kind of like a digital twin, what Chris said. And so then you use that to simulate your system, and then you learn from that, and then you deploy. So it's the sim to real approach where you simulate on the computer. Again, you need to have access to a model, so it's not really one that we can use, but then you can again optimize it and then have the adaptability feature of RL. If you do get into learning, you'll read about Q-learning. It's a value-based approach, which is the most common use. It's the simplest one to understand. Over time, and again, without going into detail, the soft actor critics are really good, which is what we're using. It's a mix between policy and value-based optimizers. And the reason they're also very good is because they are sample efficient compared to the others, so they don't need as much data as the other ones. And you can use them for continuous state and space action spaces. So you can use sensor readings directly, and your actions don't have to be discretized, which is a good thing. Otherwise, your space explodes very quickly. So I won't go too much into detail at that at all, but if you need these names, we use soft actor critics in our work. We have this paper that we just put out a few weeks ago with all kinds of experts in the field. So if you're interested really in building energy control with RL, this is the state of the art, summarized and open questions where we think the field is going. So you can get an overview of that. It is very much demand side focused. So I'm not looking at right now, things like power plant dispatch problems, but of course they're all related to some extent. At some point, they need to be moved together. We're mostly looking at the demand side here. Okay. Oops. There we go. So okay, so we know now we need to do that. We're interested in these grid interactive problems. We want to simulate many buildings. We want to see how they interact with a grid signal, reduced signal or carbon content in the grid. But when I started this 5-6 years ago, when I started at UT, there was no way to simulate that. There was always Energy Plus, but it's very clunky and it's not meant for this. And I suffered once through doing a co-simulation environment with different top simulators, and that's just not something you can easily scale or give to other people to work on. And so, in the first 2 or 3 years, we literally didn't do any research. We just created the simulator that would allow us to do that. So we call that CityLearn. We built everything into a single platform, simplified a bunch of things, made in a few assumptions. But essentially what we can do now is create, very cool building models. Mostly we look at residential, any sort of systems they can have, solar, thermal, HVAC. Right now we're working on EVs, so we will have that in a couple of weeks, batteries. And so all of that combined, and then have a grid signal for them, like pricing or CO2 content or both, right? In order to react to that. And then, we can use it with smart meter data as well, because that's how it was set up. And so that way you can actually simulate the behavior of your data that you have your smart meter from, assuming you meet the demand on your smart meter that's given by shifting loads. It's kind of like the backside of this. Again, we've basically what we wanted is you don't have to deal with the building, so you don't need to deal too much with setting up an Energy Plus model or even multiple models, but you can just use what we have and you can go straight to the control. And we are not, my research group focuses on RL, but you can use MPC and you can use rule-based control. Some folks have done, comparison between RL and MPC for this type of work, which is what, using CityLearn, which is exactly what we intended to. So that's kind of cool. And that way you can be in the same environment, you can benchmark, you can release your results, and then other people can try and extend it. And again, if you're interested, it's free, open source. You can use it, enjoy it. Let us know if you need inputs, help. We're happy to help. Right now, we're working with a group in Cambridge, Dr. Ruchi Chowdhury's group, to set up something from the Cambridge campus, which is also pretty cool. So again, we're expanding and a lot of different applications. Okay, so when we have that, obviously one of the questions is what's good can we do, right? So we basically, jotted down a few challenges that we have in this one paper that says, okay, these are the big problems that we can have when we go into the real world and we start doing RL on buildings. And then you can see here, these are C9. We borrowed them from computer scientists. It's not, we didn't spend a lot of time thinking about these, but we transferred them what it means, right, for our problem. So this one here, training offline from fixed logs, basically is the interesting problem, because that means you have some sort of data from your buildings. But if it's commercial building, you may have old logs, daily data, whatever, like a building level or sub-meter level. If it's residential buildings, you may have some smart meter data. So there is some knowledge, there is some data knowledge. So the technical term is then offline learning from this data that you already have to pre-train your controller, again, without any needing a model, but you pre-train it based on that data, and then you can deploy with a lot more confidence than just generically random initialization. And so that's what we did for a while, and then we learned, right, that you can, if you start with simple rules that you have on your system, because you know what they are, you have certain initialization ways to do it, so you don't have to start from scratch. If you jumpstart with rules and you use some of these fixed logs, you can reduce the data intensiveness quite significantly, which solves a big problem. So we really didn't need to model the buildings now. We just needed the rules, simple rules that the building have. So how your thermostat might work, or how you might charge and discharge, your batteries or your other storage. And as soon as you have those, you can use the RL to optimize them for your particular demand schedule. So that's kind of cool. And again, I will say this: if you have a really, really good role-based controller, really, really good sequences of operation, there is some evidence that any sort of this advanced RL and MPC really does not win a lot over it. So the advantages of MPC and RL, or these advanced controllers, are really in the sense that you deploy something, but you don't have the time to tune it because it's a manual tuning process or manual setup, but you can let it sort of optimize over time with a good guessing start, which makes it efficient on a human resources side, basically. So that's one of the things. Then what we did, so now can we get to our initial question, right? Can we do some flexing? Can we actually learn, again, in a challenging way? So we have one building when we can learn stuff, and then we deploy in another building to flex our loads. And the short answer is yes, we can. And let me show you what we did for that. So we built this whole interface, now that Chris dropped the word digital twin, it's kind of like where this would go, right? We take data from smart meter data from a neighborhood. This is in California, about 20 buildings, and we recreate them in CityLearn, basically because we have the loads and we have the specs of their batteries and the solar panels. We know where they are. We can provide them with electricity rates, the time of use, charge, the emission of the grid on the hourly time base. And then we can optimize and basically see what if we only have data from one building, what can we learn, and then put that agent onto another building and then see how well it performs. And we do that in a sort of realistic scale. So here's the buildings. These are already very high efficiently built building to US standards. And interestingly, the report that EPRI did, this is the Electric Power Research Institute, the report they did said the batteries don't really add anything. They don't make sense. And so keep that in mind when I come back to that. So anyway, these are built to relatively high standard by US. There is smart thermostat, there is EV charging, there is electric, everything is electric, it's well insulated, battery storage, and so on, good envelope insulation, and they all have solar panels. And so again, we were looking at whether or not we can, control the battery in a smart way. And we wanted to do that in a realistic way. So the first one is to just look at the 12 months and, just find the best controller for each of the buildings. So we have a reference point for that. But then what we wanted to do is to train for the first part. We had 12 months data. So we trained for the first part 5 months here. We could do only 1 month or 2 weeks, whatever. It doesn't really matter. But we could train on one building for some date time, and then we deploy on the other building for later. And so this way we don't, reuse training data in the deployment process, which makes your results look better. So this is a real sort of like deployment strategy, right? This DS3 here. So we monitor several KPIs. So again, like I said, we use an RBC, which is a typical one. Like this is what is implemented on those buildings is, charge when it's cheap and discharge when it's expensive. This is what we all do, or we would do. And this is a simple RBC to control because you have the times and you have the, when you have to charge and you have to discharge. This is the tariff rate in Southern California. There's a difference between winter and summer, and then weekend, weekdays. So we implemented those. And then we look at KPIs on the building level, which is because that's usually what you have to communicate, reduce electricity consumption, the costs and emissions, how close you get to zero net energy, I think on a weekly basis or an hourly basis. This is a tough one. And then on the aggregated level, can you reduce the peak of all buildings, provide some support for ramping, and then the load factor, which is the peak to average ratio of your profiles. And so again, for simple terms, there's a lot of numbers here, but in simple terms, right? Obviously, if you have a lot of knowledge, DS1, that's optimal for every building. That's the best. But the DS3, which is you can actually deploy on one building, learn on one building and deploy on the other buildings, that is still better than using the simple rules for that other building that you didn't know about anything. So this means you can pre-train on one building and deploy it on another building, and it will be good. Obviously, these are all single family homes, same sort of setup, right? So they're not that much different, but they are different in their load because there's different people using them. I'm not sure if I have the slides for that, but we can look at that as well. But what is interesting is you can see the rule-based controller. Remember, this is time of use tariff. That is the standard implementation of these. Electricity demand goes up 5% compared to the no control case, and electricity cost goes down by 5%. And so this is why when you implement batteries, one of the conclusions is they don't make any sense because your demand doesn't really change and your cost don't really change. But if you have a little bit more advanced control and you actually can implement a little bit more something that's adaptive to your own needs, your own demand profile, the savings are much bigger, like 20% for cost, 15% on demand reduction. That's a lot more substantial than the other one. If you look at emissions, it's the same because demand and emissions kind of go hand in hand, at least in this data that we have. Zero net energy is a tough one in any case because demand aligning, you basically cannot get it on an hourly basis right now with the buildings we had and with the setup we had it. So that's a tough one to continue. The daily peak, obviously, if you control, you can reduce a lot more. Ramping, this is the gradient of your demand basically over time. So the higher you're ramping, the more you may need peaker plants. So again, the RBC, because all the batteries charge and discharge at the same time, you create this large demand on the grid because they're not adapting to themselves and there is no coordination between them. So that's really the bad thing here, that if you deploy these at scale, you'll end up doing some funky things on the grid that may be unintended. And the peak to average ratio did not really change for that sense. So anyway, the big ones, electricity demand reduction, electricity cost, and carbon emissions, and daily peak, they all go better if you have some advanced control rather than the basic sort of time of use control in these systems. And here's a little bit how you can see why the black curves are the individual demand profiles of the homes. The red ones are the time of use controllers. You see the charging and then the discharging later. So you do get a big relief in the afternoon, but then you also have a smaller peak or an earlier peak during the day. And you can look at the black curves. You can ignore 15 and 12 because they're kind of like weird. But the other ones are very individual. You have some that are, this one here rather constant or, not a lot of change. You have this one that have an early peak and then completely no peaks or a big trout and then a big valley, and then another peak in the afternoon. And so what happens is that the green controller, the RL controller, can really adapt to that. And if you look at the green curves, they're all rather constant, right, compared to the other two. And that's kind of like where we're wanting to go. Remember, this is when you aggregate everything. So of the 18 buildings, you aggregate them, you see you actually increase the peak of the grid because you charge everything at the same time without controlling and coordinating. So that's what I mentioned, that this is kind of like a drawback of the time of use control. The same thing happens when you have smart thermostats that starts to preheat your homes in the morning. Similar study has been done in the Boston area, and like hundreds of thermostats start at the same time, and boom, huge peak on the grid. And so there is need for coordination to achieve the intended support that these devices can bring. But if you do that, you look at the blue curve, you look at our green curve. I should color coordinate this a little better, but this blue curve that I showed you in the beginning, starts to look a lot like what we want to achieve, which is a lot more smooth, a lot more constant. Maybe you don't get the same same large supply back to the grid during the time when you don't need it. But then in the afternoon and the early evening, when you do need the grid support, you don't have the same high peak as before. So you can really flex, which is pretty cool. And then the really cool part, and there have been like 2 or 3 studies, like just in the last few weeks, that came out, and this is from economists, an economical group, Brattle Group, that said, well, this kinds of virtual power plant operation, you see on the right, you could equate, because now you have basically a grid, a power plant that is distributed across everything, and you could equate that with building more infrastructure. So building a new gas plant, building a grid scale battery, or building transmission. That all has costs, and it provides you some services, right? But you can equate that with virtual power plants, where you have different costs, different services, but at the end, you will provide the same sort of like energy to your area at a lower cost. And so there was another study out of Stanford just like a week ago that basically said the same thing. There was a similar study in Switzerland that said the same thing, that compared battery PV operation, and then grid transmission, distribution, expansion capacity, and OPEX and CapEx. And so those things, again, like I said, as they start to like converge and you start to basically weigh them against each other. In the US, transmission expansion is pretty tough. And so maybe these are kind of like the solutions that locally people look for to address the flexibility need that we have. Alrighty, so I think that's it. We just released a V2 version of CityLearn, like again, a month ago or so, which is a lot better in many ways. I won't say a lot about it, so we can have a chat. Basically, more systems, more buildings. We interface with NRELs and data, an end user load profile database for the US, so we can have typical loads in the US and typical neighborhoods in simulation. So that means we can run these. And we can have like an actual understanding of what the loads would be in different areas of the US. I have a grant proposal with folks at UCL to do similar stuff for England or Europe, so that we can actually understand the differences, but we need the end use load profiles for that area. And we're working currently with a group in Portugal, as I said, to integrate electric vehicles, which has been always a missing link, but a very interesting link, because many folks are using that. To do that. If you want to get started, 12 lines is all you need. Sorry, 18 lines is all you need. It's very easy. We have a tutorial, a walkthrough. You can run to your first RL model rather quickly and get rolling, and then take it from there. We spent a lot of time, like I said in the beginning, to make it usable to others, because I didn't want to write code for our own sake. But if nobody else can use it, it's kind of pointless. And so that's why a lot of the time we just extend and interface with standard libraries. Alrighty, this is where I stop. Thank you for listening, and I'll take some questions.
Thank you so much, Zoltan. That was really, really nice. We do actually have some questions in the Q&A. I'm just going to go through them. So the first, we've seen improvements in applying stochastic MTC and can improve the control of batteries for highly uncertain demand. How does this compare to reinforcement learning, which I perceive as being more like deterministic / point-based control? And or is there some adjustments?
Yeah, I mean, stochastic MPC is one of those that I mentioned is where the MPC part becomes a lot more, stochastic. So you don't know what to expect, but you still need the models, right? You still need to understand how stochastic your environment is in order to be able to make those optimal decisions. So they are similar, but they're not the same.
Cool. I just have a quick question as well. When it comes to
Yeah.
data that is from home, so like load data, consumption data, it's not always perfect. You get missing values, you get like erroneous readings. How does reinforcement learning deal with this? Is that an issue, like when it comes to deploying them, deploying reinforcement learning agents? Yeah.
Yeah, I think that, I mean, that's a good question. And that's kind of like, when I start my machine learning class, I say, we're going to do the machine learning part, and that's cool. But in reality, you're going to spend 80% of your time cleaning your data and then 20% of your time doing the machine learning part. And that's not different here either. Like data quality itself needs to be done. Of course, I think that you don't really win anything by that. We will. So we're about preparing the CityLearn challenge, and we will do that this year. We'll give Errorless Data to see what good sort of pre filters are useful for doing that easily. So that's a more realistic problem.
Okay.
But the method itself does not help with that.
Okay. Cool. Cool. We have loads of questions, so I'm just gonna razz through them. So, what characteristics do you look for in a problem to indicate that reinforcement learning will be likely a good methodology in comparison with rule-based control or MPC or other?
Oh, that's Patrick. Yeah, hi, Patrick.
Yeah.
I think the so there are two characteristics. So first of all, RL is useful in what's called sequential decision making problems. So that's another term for control, but maybe not in the control area. So things like any sort of planning problem where you make decisions over time. That's kind of like where these things happen to work really well. Again, RL is really good when it's hard to create the models. So in some sense, either the system is too complex to create the physical models, or it's not a physical problem, in which case there is no physical models, right? So that's another way. I don't know if NRBC is basically how well is a problem understood and how well is it performed. So if there is an indication that we are needing to optimize, then that's why you would use an optimizer like RL.
Great. Yeah, that makes sense. What have you found to be the blockers to implementing this work in practice?
Yeah, one. So there's two. I mean, not two. I don't know. Let's start. We'll see where we go. The one big one is the one that Chris mentioned, which is the black box nature. So in MPC, we know exactly what will happen. It's just very tedious to do it. It will take you a couple weeks, months, even years to get to that model and then implement it. In RL, you could do it very quickly, but you may not know what it's doing. And so when you go to a building manager and say, we're going to do something to your building, but we don't know, the agent will explore, then it's a pretty quick stop at that discussion. Especially if you don't have a relationship. Now, I know, in you mentioned DeepMind, Chris. I know Google is doing these experiments in the buildings. They know, like, oh, we're going to run it because it's cool and we can learn something, and the people are on board. So that's sort of like a communication problem. It's not a technical problem. There's always a little bit of a technical problem to interface and make it workable with all the legacy BMS systems, but those are solved if you have the money and the manpower. The biggest one is really communication with the people to make it work.
Yeah, I think that's a really good piece of advice there, making communication open as you're implementing these solutions.
If you're interested in this question, last year at the RLM workshop, you can Google it on YouTube. You can find a very good discussion between Gregor Henze from Boulder and Troy Harvey from passive energy, passive logic, who are implementing a new type of AI control. That this was basically an hour-long discussion. Why don't we have smart buildings? Or what's the big deal? What are the big challenges? So I can recommend that for anybody. It's on YouTube.
Yeah, no, that's really interesting. I'll definitely take a look at that.
Yeah.
Okay. What simulator are you using for modeling heating, ventilation, air conditioning systems with high configurability? Is that contained within CityLearn?
Exactly. So that's what we did from the beginning. So we wrote the simulators ourselves. So those are physics-based models of the HVAC systems, of the solar systems, of any of the systems we have, so that everything is contained in Python. And so, and same with the building models. And so that's one of the things where, if you want sort of like a certified model, it may not be the case. It's not an Energy Plus simulation. It's somewhat simplified, but it is based on physics, so hopefully not too far off.
Cool. There's a practical question. Can I apply CityLearn to my own house to optimize my energy consumption?
You can do that. Call me. Interesting to see. Yeah, you can do it with a single building. Obviously, it would be interesting to see how it would happen. What we could do. I think if there is some smart meter data and there's some opportunities to do scheduling or do some simulations in that, might be interesting to explore. Yeah.
Cool. Yeah. Fantastic. What type of assumptions did you have to make for CityLearn?
Well, that is a broad question. Yeah, I mean, like I said, we made simplification assumptions on the systems so that we can actually implement everything into a single interface, right? So that came with a few assumptions on the linearity of the models and things like that. I don't know if that answers the question, but
Yeah, I didn't really.
if you're interested in this topic, so there are two other projects that I should have mentioned. So there is Bobtest, a BIPSA project that implements an Energy Plus sort of like grid interactive control simulator. You can go and try that, and that's kind of like the control interface that DOE now is pushing to use with Energy Plus. And so you can try that, and that gets you into like a more standardized sort of interface in some sense, or a known interface. And then the other one is called the Advanced Control Testbed, ACTB, which is again done by Dr. Henze in Boulder. And that is similar, uses Energy Plus or spawn of Energy Plus in the middle, and then has all kinds of plugins to bloat it up a little bit. It's a co-simulation environment, but there is more to play with. And then the academic world is a lot, like Chris, like there's a lot of projects in the last 3-4 years that were like, oh, here's Energy Plus, here's a Python wrapper for Energy Plus, and then we can run RL around that. There's tons of those, but they're hard to replicate on your own. So this is why we wanted to avoid that kind of wrapper situation.
Great. Okay, we've got a upvoted question here. How do you go about defining correct or most? Oh, here we go. How do you go about defining correct or most valuable during training for the reinforcement learning models managing residential buildings? I'm not sure.
I don't know what that means. So what we're looking at is we're looking at the behavior. So we have our reference controller, the RBC, and we look at we visually inspect the load curves that come out of the RL controller. There is no, so actually that's an interesting question in another way, and maybe that answers it. So the reason we'll look at, let's say, 6 or even more KPIs is precisely because there is no correct way of looking at it, I think. So you can look at, do you reduce the energy use? That's one thing, but that might be counterproductive with, let's say, the overall behavior of the neighborhood. And so that's why we look at that as well. Maybe you're interested in emissions, but then maybe that leads to another one over there. And so that's a good question in that sense, that there is no such thing, and your optimizer needs to reflect that as well when you do that, right? So that's actually a brilliant question in hindsight.
Yeah, that is awesome. Oh, we might have lost Zoltan.
Oh,
He's coming back.
okay.
There we go.
Sorry.
Okay. No, all good. I think we have time for one more question. Based on your presentation, it seems like the smaller the peak, the better, but maybe it's not bad if the peak is at the right time. For example, all the batteries start charging when there is plenty of wind power, which obviously raises the peak.
Yep. No, that's a correct observation. And again, in that particular example, when the peak was during the middle of the day, if we had the actual sort of solar generation at the time, maybe it would have been fine on sort of like energy wise. And this is where now it's interesting to interface with grid and distribution, because maybe you on the other hand, while the energy might be fine, but you may be having too much power draw at that time, so you need bigger wires, right? So this becomes another issue. But I agree that time wise there may be a better time to demand to create demand, and in order to offset it later. So that's totally correct, which is why we need to look at it together with the supply side.
Yeah, nice. And I will just squeeze in one more question. Here we go. Is CityLearn used to investigate situations in the real world at the moment, or is it most likely to be down the track in the future that